Classification of matter. So what is matter? Not what's the matter, but what is matter? When scientists talk about matter, we're talking about something that occupies space and has mass. So there's lots of examples. Your book, your desktop, your desk, your chair, your body, all matter, okay? Is the air in this room matter? Yes, it is. Does it take up space? Well, have you ever blown up a balloon, put air into a balloon? It takes up space. It doesn't appear to have mass, but we can show that it does have mass. So air is matter. How about love? Is love matter? No. Love matters, but it's not matter. Love is an emotion, right? It doesn't take up physical space or have physical mass. So we use the word substance a lot. When the scientist says substance, we mean a specific instance of matter, a particular kind of matter. So I could say that this pen is a substance. The soapy water in this wash bottle is a substance. Okay? So it's just a particular kind of matter. Well, scientists try to make some order out of the universe by putting things into categories. Again, with the Lego blocks. Because we've been collecting Lego blocks for about 22 years, and so we have tons of them. They have taken over the dining room. And every once in a while, we get this crazy idea that we're going to organize them so that we can find the pieces we need. There's so many different ways you could organize Lego bricks, right? You could organize them by color. You could organize them by size. You can organize them by what set they originally came from. You get the idea. So matter, physical matter, can be separated and categorized in different ways as well. One way to do this is to classify it according to its state. Not California or Arizona, but its physical form. Is it a solid, a liquid, or a gas? We could also classify it by its composition. What is it made of? The basic components. So let's look at the states of matter. Solid, liquid, or gas. There are other states of matter. We're not going to talk about them because they're very rare and unusual. We're going to talk about solid, liquid, and gas. If you think about water, we are familiar with water in all three of its physical states. As a solid, we call it ice. As a liquid, we call it water. And as a gas, we call it steam or mist or fog or humidity. We are familiar with them. If you take a solid and you increase its temperature, you can probably melt it into a liquid, increase its temperature further, and it will form a gas. And so here in this illustration, we're looking at the particles in the solid, the liquid, and the gas. In a solid, the particles are very close together, and they don't move relative to each other. In a liquid, the particles are also close, but now they're kind of, swimming around each other. They're mixing and mingling, okay? In a gas, the particles are very far apart from each other, and they're moving independently of each other. So I like to talk about the three states of students. Right now, y'all are in the solid state. You're sitting, right? Some of you are unfortunate enough to be standing because we don't have enough chairs. You're not moving relative to each other. Are you all perfectly still? No. I hope everyone's at least breathing, right? Please do not die in my classroom. Hasn't happened yet. Perfect record. But you're moving, you're looking around, you're blinking, you're swallowing, maybe taking notes, right? So there's movement. The particles in a solid are moving. They're just not moving relative to each other. The liquid state of students is when we have lab. We all stay in this room. We're still very close to each other, but now we're moving around. And you may start out over here by the hoods, then you have to walk over there to the balance and get something, and everybody's moving around. That's what a liquid is like. The gas state of students is when class is over and you all diffuse out the door and you go off in your separate directions, and many of you will not interact with each other at all until you come back to the solid state for class on Wednesday. Okay? So here's more words. I'm going to go through this quick because I already talked about it. So in a solid, molecules are very close to each other. They vibrate, but they don't move around relative to each other. So a solid has a fixed volume and a rigid shape. Its shape doesn't change. Think about an ice cube. If you take an ice cube from a tall, skinny glass and put it in a bowl, does its shape change? No. Does its volume change? No. It's just its own little ice cube. We can categorize those solids, break them into two broad categories, crystalline or amorphous. So crystalline, the atoms or molecules in there have patterns with a long-range repeating order. So here's an example, a diamond. These carbon atoms are arranged in a very particular way, and this pattern extends in all dimensions, all three dimensions. Okay? So this is a crystalline solid. Another example is table salt. Go home and look at the table salt. It's these little teeny tiny cubes. Do you think that Morton spends a lot of money and energy making your salt into beautiful little cubic crystals? No. That's the way salt wants to be. They're just not fighting nature. So those are crystalline solids. Amorphous, we do a lot in science with prefixes and suffixes. A is a prefix that means without. Sorry, I'm drifting here. Amorphous, morph referring to shape. I sometimes fight with my iPad. I'm having a battle here. Amorphous, without shape. So the molecules have no long-range order. Examples of this are glass and plastic. There's no long-range order. Liquids, again, the molecules, the atoms are very close, but they move relative to each other. So liquids have a fixed volume, but their shape will change. You take a 1 cup measure of water and you pour it into a bowl. The shape of the liquid water will change. If you take it from the bowl and pour it back into the cup, it's the same volume though. The volume won't change. Okay? The liquids can flow because the particles can move relative to each other. Solids can't do that. And then in a gas, you've got lots of space between. And so gases will change shape. They will also change volume. So here we have two illustrations, a solid inside this piston and a gas. In a solid, the particles are already touchingly close. And so if you put pressure on this piston, you cannot squeeze them together. It's like Lego bricks. You fill up the bottom of the Lego bricks and you stamp down on them, you can't compress them anymore. But if they're scattered all over the place, like a gas with lots of room, you can compress the gas and force the pieces closer together. So gases are compressible. Any questions? So that was classifying by state. This is classifying by composition. So here's a chart that gives us an overview here. We've got matter. We can look at pure substance versus mixture. And then pure substance is divided into elements and compounds. Mixtures are divided into heterogeneous and homogeneous. So pure substance versus a mixture. In a pure substance, all of the individual particles are the same. So we could have, let's pretend that's chlorine gas, Cl2. And so all of the particles are the same. 2 chlorine atoms stuck together. That would be a pure substance. In a mixture, you might have different kinds of atoms. So you might have green ones. I did not choose this example very well. And red ones. I'll probably do it better tomorrow. The individual particles are different. You can have a pure substance with these 2 red and green. Let's do it over here. We need some divisions here. So this is a pure substance. This is also a pure substance. Each of the particles is composed of two different things, but all of the individual pieces are the same. That's a pure substance. This is a mixture because we have different particles. We have green particles and we have red particles. Does that make sense? In a mixture, you can have different proportions. Here I have an equal number of green and red, but I could throw another red one in there. Let's do that. I could throw a couple more red ones in there. It's a mixture. I can vary the ratio of red to green. Over here in this pure substance, if I put a red one in, I also have to have the green one that's attached to it. So the composition of a pure substance is always the same. The composition of a mixture can vary. Those pure substances can be broken down into two categories, elements and compounds. And this has to do with whether you can take those molecules or atoms, those smallest particles, can you divide them into two simpler substances or not? Don't know, I thought there was a picture. So let's stick with my not so great analogy. So let's look at, I had these molecules and I had these molecules. Could I take these two atoms apart? I could. If I took that apart, I'd end up with a green one and a red one. And those are different. So this is not an element. This is a compound. It can be decomposed into simpler substances. What if I take this one apart? Now I've got two green atoms. Are those simpler than that? Not really. These are two green atoms. They're just not together anymore, and this is two green atoms. This is a red and a green together, and now I can separate that, and I could divide the red and the green into separate containers and end up with two different substances. That was not very good. We'll just go on. So elements cannot be broken down into simpler substances. These are the building blocks of matter, the Lego blocks. So something like helium. You fill a balloon with helium. All the particles in the helium gas are the same. They're helium atoms. It's an element. A compound is a pure substance, but it's composed of two or more elements that are combined together in a fixed proportion. Most elements will react with each other and they will form compounds like water, sugar, all kinds of different things. So an example of a compound would be something like, I started with the wrong color, something like water, which we usually represent with two white balls and a red ball. So there's always one oxygen atom, two hydrogen atoms. All water molecules are the same. And you can decompose it into oxygen and hydrogen. So it's a compound, it's not an element. Any questions? So that was the pure substances. And then the mixtures we can also break down into two categories, homogeneous and heterogeneous. Okay, and there we've got prefixes. And if we understand what the prefixes mean, it's easier to understand what these words mean. Hetero means different. Homo means the same. Okay? We break this down by how uniformly the substances in the mixture mix with each other. So these are talking about mixtures. You've got at least two different substances mixing together. Do they mix very well? It's homogeneous. It's the same throughout. Or do they, just kind of clump together and you can see there's obviously two things mixed together. That's heterogeneous. An example of a heterogeneous mixture would be salt and sand. Mix salt and sand together. You can stir it all you want. You look at it. You can see the salt crystals and the sand grains, right? They're not going to mix intimately. Another example would be oil and water. Put oil and water together, shake them up. You can get it to mix for a little while, but as soon as you stop shaking, all the oil's going to rise to the top and all the water's going to sink to the bottom. Two distinct layers. It's heterogeneous. There's two different parts. Those different parts in that heterogeneous mixture have different compositions. They have different properties. The oil on top is very different from the water underneath. In a homogeneous mixture, you have multiple substances, but it appears to be a single substance. So an example would be sweetened tea. So you've got your black tea without anything in it, and you have your white sugar. Two different things. You put the sugar into the tea and you stir it up. What happens to the sugar? Can you see it anymore? It dissolves. It seems to disappear, right? You put it in there, you stir it all up, you can't see it anymore. It's gone. No, it's there. It just mixed thoroughly with the water in the tea. If you sample the top of the tea, the middle of the tea, the bottom of the tea, it's all equally sweet. Okay, so that's a homogeneous mixture. It's going to have a uniform composition. The composition, the properties of the top layer are going to be the same as the bottom. Another example of a heterogeneous, if we think about soup, okay? So chicken noodle soup or cream of tomato soup, which one's homogeneous? Cream of tomato. And you make it homogeneous because you stick it in the blender and you grind everything up until it's all in little teeny tiny pieces. The chicken noodle soup is heterogeneous. You can see the pieces of chicken, you can see the noodles, and you can see the broth. Different composition, different properties. Okay, so mixtures can be separated because the different components in them have different physical or chemical properties, and we can take advantage of those differences to separate them. There's lots of different techniques. We're just going to talk about a couple of them. If you have a mixture of sand and water, you can separate them by decanting the water. So imagine, I'll draw it. You'll see why I did not go into art. I am a functional drawer. I'm pretty good at Pictionary, but let's see. That'd be a good color for sand. Oops, that's too small. Let's see. Oh, that was too big. That's okay. There's the sand at the bottom of the water, right? You could stir that up, make a mess out of it, and you let it sit, and the sand will settle to the bottom. Decanting means that you take this beaker and you pour the water off carefully so that you don't disturb the sand on the bottom. And you can separate most of the water from the sand by doing that. Because the sand is a solid, and it's more dense than the water. The water's a liquid, and it's less dense. So it's on the top, and it will pour off, and the sand won't. Using the different physical properties of the substances to separate them. Another method is distillation. So here's an illustration of a very simple distillation apparatus. So here we have a round-bottom flask with a mixture of different liquids. And this is exactly the way that they distill alcohol. Okay, so you can make alcohol by taking anything with sugar in it, hops or grain or wine or almost anything, and letting it ferment. The bacteria will turn the sugar into alcohol, so then you have a mixture of alcohol and water and all this other stuff. How do you get the alcohol out? Well, you distill it. And when they made moonshine in the hills, they called them stills, okay, short for distillation apparatus. So you heat this. The alcohol has a lower boiling point. It boils at a lower temperature than the water does. So as you heat this, the alcohol will boil and go into the gas state. Now that's the part that you're trying to capture. So you don't want that just to go out into the air. So it comes up here, and then you make it go through this tube called a condenser. This is a double-walled tube, and we run cool water through it to cool the alcohol and cause it to condense. It condenses back into a liquid, and then it drips down in here. And so you can collect the pure alcohol over here. Distillation is used for all kinds of things. It's used to separate crude oil into all the different useful components of it. There's many, many uses. So it can separate liquids that have different boiling points. The more volatile liquid will boil off first. Volatile means it's easy to vaporize. So that's distillation. Filtration. This is something that you've probably used in your kitchen. Have you ever made spaghetti? You put boiling water, get some boiling water, you put the spaghetti in there, and then you have to separate the spaghetti from the boiling water. So you get a colander, a bowl with holes in it, right? Stick it in the sink. You pull the whole thing into the sink. The boiling water goes through the holes in the bowl, the colander, and the spaghetti doesn't because it's larger. The boiling water is a liquid. The spaghetti is a solid. This is what it might look like in the chemistry lab. We're going to use a funnel with a filter paper, a lot like a coffee filter. This is how coffee is made also. And here we have a mixture of a liquid and solid. If you're making coffee, you've got hot water with coffee grounds in it, and the good stuff of the coffee comes out into the hot water, and then you want to get rid of all the coffee grounds. They're kind of like sand, right? So you pour this mixture through a filter. The coffee, with all of its yummy flavors, goes through into the beaker, and the coffee grounds that are solid stay behind. So that's filtration.